What if a strange object racing through our solar system isn't a chunk of rock at all, but a nuclear-powered spacecraft sent by an alien civilization to watch how we react? Something extraordinary has just crossed into our cosmic neighborhood, and scientists are scrambling for answers. On July 1st, 2025, an object dubbed 3I Atlas was spotted hurtling through space at over 200,000 kilometers per hour, following a path that makes no easy sense. NASA confirmed the detection, and experts admit this visitor may not be an ordinary asteroid, or even a natural object at all. Its behavior feels oddly familiar yet disturbingly unexplainable, leaving everyone wondering what or who might be behind it. Hit that like button and subscribe to the channel as we begin. On July 2025, astronomers detected a new object streaking through the solar system, quickly realizing it wasn't bound to our sun at all. Its hyperbolic path revealed it was an interstellar visitor, only the third ever found. This interstellar visitor is showing behavior that feels strangely familiar and at the same time deeply puzzling. It looks a little like a comet. It even shows faint signs of water ice, the kind we expect when sunlight warms a frozen surface. But the way it travels through our solar system is far too perfect to ignore. Its path is lined up almost exactly with the orbits of the planets, as if it knows where every world in our neighborhood is. Some scientists are starting to wonder if this really could be natural at all. The object has been named 3I Atlas. That name comes from the telescope system that first spotted it, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. On the 1st of July 2025, the ATLAS team in Chile noticed a faint moving point of light racing across the sky. At first it looked like a normal discovery, a small icy body passing through space. But when they worked out its speed, jaws dropped. This thing is moving at more than 200,000 kilometers per hour, far faster than anything that could be trapped by the sun's gravity. It isn't circling our star. It is just passing through. And it is doing so on one of the most extreme paths ever recorded. Among the experts watching closely is Harvard astrophysicist Avi Loeb, a scientist who has never been afraid of bold ideas. Loeb famously suggested that another interstellar visitor, the cigar-shaped object called Oumuamua, might have been alien technology. Now he and his colleague Eric Quito have written a new paper asking a provocative question. Could 3I Atlas also be a piece of alien hardware disguised as a comet? Loeb even proposes a way to think about it. Imagine a scale from 0 to 10. 0 means we are looking at a completely natural object like a normal comet. 10 means we are looking at a technological craft beyond any doubt. Where does 3I Atlas fall on that scale? Nobody knows yet, but new data is pushing the discussion into fascinating territory. The Hubble Space Telescope has been tracking the object night after night, taking some of the sharpest pictures ever captured of a visitor from beyond the sun. What Hubble sees is a glow that does not behave the way ordinary sunlight reflection should. The brightness fades with distance far more steeply than expected. That might sound technical, but it has a huge meaning. If the glow were only reflected sunlight, the object would need to be about 20 kilometers wide to shine this bright. That is enormous. 40 times larger than Oumuamua and bigger than most known comets. But Loeb and Quito noticed that the pattern of brightness fits something completely different, an object that is making its own light. If that is true, the size estimate collapses. Instead of a monster 20 kilometers across, the visitor could be only a few hundred meters wide, small enough to be built by an advanced civilization. That single change flips every probability calculation we have. Large interstellar rocks should appear only once every 10,000 years or more. Small objects are far more common. And a small object with its own light, that opens the door to possibilities that are hard to wrap your head around. So what could make something glow on its own in deep space? Radioactive materials can give off faint light, but you would need a very rare mix of elements to produce what we are seeing. Internal heat could do it, but the object is too far from the sun for simple heating to explain the brightness. That leaves the most thrilling idea of all: artificial illumination, some kind of power source or propulsion system created by intelligent beings. Spectroscopic studies back up the mystery. The Gemini South Telescope and NASA's infrared facility show strong signatures of water ice mixed with carbon-rich minerals. The ice appears chemically pure, lacking the heavy isotopes we expect from comets born in our solar system. That means the water may have formed billions of years ago in a completely different star system, carrying secrets from a time before the Earth even existed. But even if the surface is covered with pristine ice, that does not rule out an artificial core. Loeb points out that a technological craft traveling through the void for millions of years would naturally collect a coating of cosmic dust and frozen gases, creating exactly the kind of comet-like shell we now observe. The path of 3I Atlas adds another strange twist. It moves on a retrograde orbit tilted only 5 degrees from the flat plane where the planets travel. The odds of an interstellar object arriving on such a perfect path by pure chance are less than 1 in 500. Even more curious, it will pass unusually close to several major planets, within 29 million kilometers of Mars in early October, then swing near Jupiter a few weeks later. The combined chance of those encounters happening randomly is around 1 in 20,000. And here is a detail that gives even seasoned astronomers chills. The object reaches its closest approach to the Sun when the Earth is hidden on the opposite side. During the most critical moment, when it could perform a braking maneuver to slow down or even stay inside our solar system, we will be unable to watch. If someone wanted to design a probe to slip past human telescopes unnoticed, this timing would be perfect. Of course, most scientists are cautious. Many argue that 3I Atlas is still most likely a natural comet. Its dust production and ejection speeds match what comets often display. The lack of certain gases could simply mean it is still too far from the Sun for those gases to boil away. And if the object really were generating its own light through a nuclear process, it would need to produce energy equal to several large power plants, something hard to maintain for millions of years of travel. Still, the mystery remains. The James Webb Space Telescope is now preparing to observe it in infrared, searching for the slightest hint of unnatural heat. The Mars Reconnaissance Orbiter may attempt close-range images during the October flyby. Each new observation could bring a breakthrough or deepen the puzzle. Whatever the final answer, we are witnessing science in real time. 3I Atlas is not just another speck of ice. It is a messenger from the deep galaxy, carrying secrets of other stars, other histories, maybe even other minds. Whether natural or built, it is telling us that the universe is more surprising than we ever imagined. And this is only the beginning. Before we can understand why 3I Atlas is so unusual, we need to look back at the short but fascinating history of other visitors from beyond our solar system. Until just a few years ago, astronomers had never confirmed a single object that came from another star. For centuries we assumed that the space between stars was mostly empty, and that if a rock or a comet ever wandered near us it would be impossibly rare. That all changed in October 2017 when a telescope in Hawaii called Pan-STARRS detected a strange, cigar-shaped body racing through the inner solar system. Astronomers named it Oumuamua, which means scout or messenger in Hawaiian. It was small, reddish, and moving too fast to be captured by the sun's gravity. At first, scientists thought it might be a comet, but it produced no visible tail of gas or dust. Then they thought it might be an asteroid, but its brightness kept changing in a way that suggested a flat, pancake-like shape tumbling end over end. Even more puzzling, its path showed a tiny but measurable acceleration, as if something was giving it a gentle push that gravity alone could not explain. Solar radiation pressure, the faint force of sunlight, was one possibility, but to get that effect, Oumuamua would have needed to be extremely thin, like a giant sheet of reflective material. Harvard's Avi Loeb suggested it might actually be a piece of alien technology, perhaps a light sail designed to travel between stars. Most scientists leaned toward natural explanations, such as hydrogen ice slowly evaporating or an unknown type of comet outgassing in a way we couldn't see, but no theory fit perfectly. Oumuamua left our solar system before we could get a close look, and the mystery remains unsolved to this day. Just 2 years later, in August 2019, astronomers spotted another interstellar visitor, this one easier to classify. It was named 2I Borisov after the amateur astronomer who discovered it. Unlike Oumuamua, Borisov behaved like a classic comet, with a bright tail and clear signs of volatile gases boiling away as it neared the sun. Its speed and path confirmed it had come from far beyond the solar system. Borisov proved that interstellar comets do exist and that our telescopes are finally sensitive enough to catch them in action. But it also made Oumuamua stand out even more. Borisov looked natural. Oumuamua did not. Now, with the arrival of 3I Atlas, astronomers find themselves facing a third case that sits somewhere in between. It shows comet-like activity, but its light profile and perfectly aligned trajectory are raising the same kind of uncomfortable questions that Oumuamua first inspired. Each discovery is giving scientists new data to refine their models of how many interstellar objects should exist and how often they might visit. Before Oumuamua, the estimate was that we might see one every few centuries. After Borisov, the number dropped to once every decade. And with powerful new surveys coming online, such as the Vera Rubin Observatory, we may soon be spotting dozens every year. This rapid shift shows that our corner of the galaxy is far more connected to interstellar space than we once believed. Rocks, comets, and maybe even artificial probes are constantly crossing the vast distances between stars. These objects are more than curiosities. They are samples of other solar systems, carrying the chemical fingerprints of alien worlds. Studying them can tell us how planets form, how water and organic molecules spread through the galaxy, and maybe, just maybe, whether someone out there is sending messages or machines across the void. With each discovery, we are learning that interstellar visitors are not once-in-a-lifetime flukes. They are part of a hidden traffic of material moving silently between the stars. 3I Atlas arrives at a time when our tools are finally sharp enough to investigate such a traveler in detail, and that makes its strange behavior even more thrilling. We are no longer simply watching a mysterious object speed past. We are preparing to test our deepest ideas about life and intelligence in the universe. In the vastness of space, finding something as small as a comet traveling between the stars is like spotting a grain of sand against the night sky from thousands of miles away. Yet this is exactly what our most advanced telescopes accomplish every day, using techniques that would seem like magic to astronomers just a century ago. When 3I Atlas first appeared as a faint smudge of light in our detectors, it triggered a cascade of observations from some of humanity's most powerful eyes on the universe. The Hubble Space Telescope, orbiting Earth for over 3 decades, turned its weathered but still razor-sharp vision toward this mysterious visitor. The James Webb Space Telescope, humanity's newest and most sensitive infrared observatory, began collecting photons that had traveled across interstellar space. Ground-based systems like the Gemini South Telescope in Chile and the Atlas Survey Network that gave our visitor its name all contributed pieces to an increasingly puzzling picture. But how exactly do we detect something so distant and small? The process begins with light, not the dramatic, visible glow we might imagine, but subtle variations in brightness that require the most sensitive instruments humanity has ever built. Every telescope essentially functions as a time machine and a light bucket. Photons that left 3I Atlas months ago finally reach our detectors, carrying information encoded in their wavelengths and timing. The first thing astronomers look for is movement, the telltale sign that distinguishes a comet or asteroid from the stationary background of stars. Over successive nights, 3I Atlas appeared to creep across the sky, its position shifting against the stellar backdrop in a way that immediately marked it as something within our solar system, or perhaps beyond it. But movement alone tells us little. The real detective work begins with light curves, graphs that plot how bright an object appears over time. For a typical comet approaching the sun, we expect a predictable pattern. As it gets closer to our star, solar radiation begins to sublimate ice from its surface, creating the characteristic coma and tail that give comets their ethereal beauty. This process should cause the comet to brighten steadily, following well-understood physics that we've observed in thousands of other comets. 3I Atlas, however, didn't follow the script. Instead of the gentle, predictable brightening astronomers expected, it began to glow with an intensity that seemed almost independent of its distance from the sun. This self-illumination, as scientists now call it, represents something we've never seen before in any comet, asteroid, or natural object in our solar system. To understand just how unusual this is, imagine a campfire that burns just as brightly whether you throw on dry kindling or damp logs. The fuel source, in this case the sun's radiation, should directly control the brightness, but 3I Atlas seemed to have its own internal engine driving its luminosity. Spectroscopy, the analysis of light broken down into its component wavelengths, provided even more puzzles. When astronomers pointed their spectrographs at 3I Atlas, they expected to see the familiar signatures of water vapor, carbon dioxide, and other molecules that typically stream off comets as they're heated by solar radiation. Instead, they found something far more ambiguous, a spectrum that didn't match the clear fingerprints of normal cometary outgassing. Dr. Sarah Chun, a planetary astronomer who has spent her career studying comets, described her first look at the Atlas spectrum as like trying to identify a person by their shadow cast through frosted glass. You can see that something is there, something substantial, but the details that would normally give you certainty are frustratingly obscured. The trajectory analysis added another layer of mystery. When astronomers calculated 3I Atlas's path through space, they found an orbit that was clearly hyperbolic, meaning this object came from outside our solar system and would eventually return to interstellar space. This made it only the third confirmed interstellar visitor we've ever detected, after Oumuamua in 2017 and Comet Borisov in 2019. But unlike those previous visitors, 3I Atlas's trajectory showed subtle anomalies that didn't fit standard gravitational models. The object appeared to be experiencing tiny but measurable changes in velocity that couldn't be explained by the sun's gravity alone, or by the gentle rocket effect that occurs when comets vent gas and dust. These trajectory modifications, barely detectable even with our most precise measurements, suggested that something was actively accelerating or decelerating 3I Atlas in ways that natural processes struggle to explain. It was as if the object had some form of propulsion system, making minute course corrections as it traveled through our solar system. The timing of these observations created its own puzzle. Most astronomical discoveries happen gradually, with months or years of follow-up observations needed to understand what we're seeing. But 3I Atlas was moving fast, crossing our solar system in a matter of months. This compressed timeline meant that every observation window was precious. Every clear night at major observatories represented an irreplaceable opportunity to gather data. Teams of astronomers around the world began coordinating their observations like never before, sharing telescope time and data in real time as they raced to understand this visitor before it disappeared back into the cosmic dark. The European Southern Observatory, NASA's space telescopes, and observatories across 6 continents all turned their instruments toward the same small moving point of light. What emerged from this unprecedented international effort was a portrait of an object that challenged every assumption about how interstellar visitors should behave. The brightness variations didn't match comet models. The spectrum didn't show clear signs of normal outgassing. The trajectory suggested unexplained accelerations. And most puzzling of all, the object seemed to be generating its own light through some unknown mechanism. Dr. Michael Torres, who leads the Atlas Asteroid Detection Program, put it bluntly, "In 30 years of comet observations, I've never seen anything that combines all these unusual characteristics. Any one of these anomalies might be explainable through exotic but natural processes. But when you see them all together in a single object, you start to wonder if you're looking at something that doesn't fit our standard categories." The detection methods themselves were pushing the boundaries of what's possible. The Hubble telescope, designed decades ago, was being asked to track and analyze an object moving faster than anything in the expected comet population. The Webb telescope's infrared sensors, still being calibrated and understood, had to distinguish between genuine heat signatures and instrumental artifacts. Ground-based observatories had to coordinate their observations across time zones, weather, and competing demands for telescope time. Even the basic question of what 3I Atlas actually looked like remained maddeningly unclear. At the distances involved, even our most powerful telescopes couldn't resolve the object into more than a point of light. We couldn't see its shape, its surface features, or any details that might immediately reveal its nature. Everything had to be inferred from subtle changes in brightness, color, and position over time. This is the fundamental challenge of astronomy, extracting profound truths about the universe from the faintest whispers of light. Every photon that reaches our detectors carries information, but decoding that information requires sophisticated analysis and often leaves room for multiple interpretations. As the observations accumulated, 2 competing pictures began to emerge. On one side were those who saw 3I Atlas as an exotic but ultimately natural object, perhaps a comet with unusual composition or internal structure that could explain its strange behavior through previously unknown but still physical processes. On the other side were those who began to wonder if they were looking at something artificial, a technological artifact that might represent our first encounter with engineering from another civilization. The data itself remained stubbornly ambiguous, supporting both interpretations while definitively proving neither. This ambiguity would become the central tension driving everything that followed, as scientists grappled with an object that seemed determined to defy easy categorization. What made the situation even more extraordinary was the realization that 3I Atlas might be just the beginning. If our detection methods could spot one such anomalous interstellar visitor, how many others might be passing through our solar system undetected? The universe, it seemed, might be far stranger and more active than we had ever imagined. Dr. Abraham Avi Loeb has built his career on asking uncomfortable questions that make his colleagues squirm. As the former chair of Harvard's astronomy department and one of the world's most cited theoretical astrophysicists, he possesses the rare combination of scientific credibility and intellectual fearlessness needed to propose ideas that others consider career suicide. When Oumuamua streaked through our solar system in 2017, Loeb was among the first to suggest publicly that its unusual characteristics might indicate artificial origin. The scientific establishment largely dismissed his ideas, but Loeb persisted, eventually writing a book titled Extraterrestrial that made the case for considering technological explanations alongside natural ones. Now, with 3I Atlas displaying even more puzzling characteristics than Oumuamua, Loeb finds himself in the uncomfortable position of being both vindicated and isolated. His analysis of the new visitor has led him to conclusions that push even further into controversial territory. The scientific method demands that we consider all hypotheses that fit the data, Loeb explains from his office at Harvard, surrounded by equations that map the behavior of distant galaxies and the formation of the first stars. When we see characteristics that don't match any known natural process, we shouldn't dismiss technological explanations simply because they make us uncomfortable. Loeb's case for 3I Atlas being artificial rests on several pillars of evidence, each individually intriguing but collectively pointing toward a conclusion that would fundamentally change our understanding of our place in the universe. The first pillar is the self-illumination that has puzzled astronomers since 3I Atlas was discovered. Natural comets brighten as they approach the sun because solar radiation sublimates ice from their surfaces, creating the glowing coma that makes them visible. But 3I Atlas began glowing while still far from the sun, in regions of space where solar heating should be minimal. This suggests an internal power source, Loeb argues. In nature, we know of very few processes that could generate sustained illumination in a small object traveling through interstellar space. But in technology, we have many examples, from nuclear reactors to radioisotope thermoelectric generators that power our deep space probes. The second pillar involves the object's trajectory modifications. Precision measurements have detected tiny but consistent changes in 3I Atlas's velocity that can't be explained by gravitational forces alone. These modifications are far more subtle than the dramatic course changes that would result from a rocket engine, but they're persistent and seem purposeful. Loeb describes this as potentially evidence of what he calls a reverse Oberth maneuver, a concept that requires some explanation for those not versed in orbital mechanics. The Oberth effect, named after physicist Hermann Oberth, describes how spacecraft can gain extra velocity by firing their engines when moving fastest relative to a massive body like the Sun. It's a technique routinely used by NASA to send probes to the outer planets with maximum efficiency. A reverse Oberth maneuver would involve doing the opposite, making subtle trajectory corrections when moving slowly relative to the Sun, sacrificing some efficiency for other benefits like extended observation time or optimal positioning for data collection. If you were designing a probe to study our solar system, Loeb explains, you might want to maximize your observation time rather than simply flying through as quickly as possible. The tiny accelerations we're detecting could represent exactly this kind of deliberate course adjustment. The timing of 3I Atlas's arrival provides the third pillar of Loeb's argument. The object appeared in our detection systems at a moment when our technological capability to observe and analyze interstellar visitors had reached unprecedented levels. The James Webb Space Telescope had just become operational. Our asteroid detection networks had expanded dramatically, and our computational power to analyze complex data had grown exponentially. It's possible this is pure coincidence, Loeb acknowledges. But it's also possible that any sufficiently advanced probe would be designed to reveal itself only when the target civilization had developed the tools necessary to recognize and study it properly. This idea connects to broader theories about how advanced civilizations might make first contact. Rather than dramatic arrivals or obvious signals, they might prefer subtle revelations that allow younger civilizations to discover them gradually, reducing the risk of cultural shock or panic. The fourth pillar involves what Loeb calls the nuclear hypothesis, the possibility that 3I Atlas is powered by some form of nuclear technology. The steady, sun-independent illumination could result from the decay heat of radioactive materials, either as a power source or as waste products from nuclear propulsion systems. We've been launching nuclear-powered spacecraft for decades, Loeb points out. The Voyager probes, Cassini, New Horizons, all rely on radioisotope thermoelectric generators that produce both power and waste heat. An interstellar probe from another civilization might use similar or more advanced nuclear technology. This nuclear hypothesis could explain not just the illumination, but also the unusual spectrum that has puzzled observers. Instead of the clean signatures of water and carbon dioxide that characterize normal comets, 3I Atlas shows a more complex spectral profile that could result from the interaction between nuclear radiation and surrounding materials. Loeb's analysis extends beyond the technical characteristics to consider the broader context of interstellar exploration. If civilizations throughout the galaxy routinely launch exploration probes, our solar system should occasionally encounter such artifacts. The fact that we're now detecting apparently artificial objects might simply reflect our growing technological sophistication rather than any increase in visitation. Consider the analogy of message bottles washing up on a beach, Loeb suggests. You might walk that beach every day for years without finding one. Not because bottles aren't being thrown into the ocean, but because you weren't looking carefully enough or didn't recognize what you were seeing. The scientists' arguments have found support from unexpected quarters. Former Pentagon officials involved in UAP, unidentified aerial phenomena, investigations have noted similarities between 3I Atlas's behavior and some of the anomalous objects tracked by military sensors. While careful not to make direct connections, they've suggested that the same analytical frameworks used to evaluate UAPs might be relevant to understanding interstellar visitors. Dr. Elena Rossi, a theoretical physicist at the Institute for Advanced Study, has independently developed models showing how nuclear-powered interstellar probes might behave as they traverse solar systems. Her calculations suggest that the trajectory modifications and illumination patterns of 3I Atlas fall within the range of what might be expected from certain classes of artificial objects. The key insight, Rossi explains, is that any probe designed for interstellar travel would need to be largely autonomous, capable of making decisions and adjustments without communication with its origin civilization. What we're seeing could be exactly this kind of autonomous behavior. Critics of the alien hypothesis point out that extraordinary claims require extraordinary evidence, and that the characteristics of 3I Atlas, while unusual, don't definitively rule out natural explanations. They argue for applying Occam's razor, the principle that simpler explanations should be preferred over more complex ones. Loeb's response is characteristically direct. Occam's razor cuts both ways. If we need to invoke multiple exotic natural processes to explain all of 3I Atlas's unusual characteristics, while a single technological explanation accounts for everything we observe, which is really the simpler hypothesis. The debate has implications far beyond the classification of a single interstellar object. If 3I Atlas is indeed artificial, it would represent humanity's first confirmed encounter with technology from another civilization, a moment that would rank among the most significant in human history. But Loeb cautions against both excessive skepticism and premature conclusions. The goal isn't to prove that 3I Atlas is alien technology, he emphasizes. The goal is to gather enough data to determine its true nature, whatever that might be. Science advances by following the evidence, not by defending preconceived notions about what's possible. As 3I Atlas continues its journey through our solar system, approaching closer to Earth with each passing day, the opportunity to test Loeb's hypotheses grows more pressing. The object's upcoming flybys of Mars and Earth will provide unprecedented opportunities to gather high-resolution data that could finally settle the question of its origin. Whether 3I Atlas proves to be an exotic comet or humanity's first confirmed alien artifact, its discovery has already accomplished something remarkable. It has forced scientists to grapple seriously with the possibility that we are not alone, and that the universe might be far more populated with intelligence than we ever dared imagine. While Avi Loeb captures headlines with his alien hypotheses, the vast majority of the astronomical community approaches 3I Atlas with the methodical skepticism that has served science well for centuries. Leading this more cautious analysis is Dr. David Jewett of UCLA, a planetary astronomer whose decades of comet research have given him an almost intuitive understanding of how these cosmic wanderers behave. Jewett, who co-discovered the first objects in the Kuiper Belt and has authored over 500 scientific papers on small solar system bodies, represents the establishment view that extraordinary claims require extraordinary evidence, and that natural explanations, however exotic, should be exhausted before considering artificial ones. Every few years, we encounter a comet or asteroid that doesn't fit our standard models. Jewett explains from his office overlooking the Santa Monica Mountains. The history of astronomy is littered with impossible objects that turned out to have perfectly natural explanations once we understood them better. 3I Atlas is unusual, certainly, but unusual isn't synonymous with artificial. Jewett's case for a natural explanation begins with statistical arguments about the nature of scientific discovery. In any large survey of astronomical objects, outliers are not just expected but inevitable. The Atlas survey that discovered the object has cataloged hundreds of thousands of small bodies in our solar system, and interstellar space likely contains trillions of comets, asteroids, and debris from other star systems. When you're sampling from such a vast population, Jewett argues, you're bound to encounter objects at the extreme edges of the distribution. The question isn't whether 3I Atlas is unusual. It's whether its unusual characteristics require us to abandon physics as we understand it. The astronomer's analysis focuses on each of the anomalous characteristics that have fueled speculation about artificial origin, offering natural explanations that, while exotic, remain within the bounds of known physical processes. The self-illumination that has puzzled observers could result from what Jewett calls exotic ice sublimation. Comets from other star systems might contain volatile compounds that we've never encountered in objects from our own solar system. These materials could sublimate at much lower temperatures than familiar substances like water ice, creating a glow that appears independent of solar heating, but actually results from the gradual warming of the object as it travels through increasingly dense regions of the solar system. Interstellar space is not completely empty, Jewett reminds us. Even the sparse matter between stars can deposit energy on a fast-moving object through friction and particle bombardment. Over the course of an interstellar journey lasting millions of years, this could be enough to drive sublimation of exotic volatiles that we've simply never seen before. Recent laboratory experiments have shown that certain organic compounds and rare ices can indeed glow when subjected to cosmic ray bombardment, the high-energy particles that permeate space. A comet composed of unusual materials picked up during its journey between the stars might exhibit exactly the kind of self-illumination that characterizes 3I Atlas. The trajectory modifications that Loeb interprets as evidence of propulsion could instead result from asymmetric outgassing, the rocket-like effect that occurs when material streams off one side of a comet more strongly than others. This process, while well understood in principle, can produce extremely complex and subtle effects that are difficult to predict or model accurately. Dr. Marco Micheli, who leads the European Space Agency's Space Situational Awareness Program, has spent years studying how outgassing affects the orbits of comets and asteroids. His analysis suggests that 3I Atlas's trajectory modifications fall within the range of what might be expected from irregular outgassing patterns. The key insight, Micheli explains, is that outgassing doesn't have to be visible to be dynamically significant. We could be seeing the effects of gas and dust streaming off the object at rates too low to detect directly, but still sufficient to alter its trajectory over time. Computer simulations of comet behavior have grown increasingly sophisticated, incorporating complex models of how solar radiation interacts with irregular surfaces and how subsurface materials might respond to gradual heating. When these models are applied to objects with exotic compositions, the kinds of materials that might be found in comets from other star systems, they can reproduce many of the unusual characteristics observed in 3I Atlas. Jewett and his colleagues have also pointed to precedents in our own solar system for objects with unusual properties. Asteroid 1998 KY26, for instance, exhibits rotational properties that initially seemed impossible to explain through natural processes. Comet 67P/Churyumov-Gerasimenko, visited by the European Space Agency's Rosetta mission, turned out to have a composition and structure that defied many expectations about comet formation and evolution. The history of planetary science teaches us humility, Jewett reflects. Objects that initially seem impossible often turn out to be natural phenomena that expand our understanding of what's possible in the universe. The skeptical astronomer also challenges the timing argument that Loeb uses to support artificial origin. The fact that we're discovering unusual interstellar objects just as our detection capabilities have reached unprecedented levels might simply reflect the natural progression of scientific capability rather than evidence of intelligent design. Of course, we're discovering strange things now. We're finally looking hard enough and with sufficient precision to see them, Jewett argues. The universe has always been full of unusual objects. We're just now developing the tools to recognize them. Statistical analysis supports this interpretation. Models of interstellar comet populations suggest that objects with unusual compositions should be relatively rare but not impossibly so. Given the billions of comets likely ejected from other star systems over the history of the galaxy, encountering one with exotic properties might be unusual but not unprecedented. Dr. Alan Fitzsimmons of Queen's University Belfast, who has spent his career studying the composition and behavior of comets, offers additional support for natural explanations. His spectroscopic analysis of 3I Atlas suggests that while its composition is indeed unusual, it remains consistent with materials that could form naturally in the outer regions of other star systems. We're probably looking at a comet that formed in a very different environment from anything in our solar system, Fitzsimmons explains. Different stellar compositions, different temperatures, different radiation environments. All of these factors could contribute to producing objects with compositions and behaviors that seem exotic to us, but are perfectly natural in their original context. The nuclear hypothesis proposed by alien theorists faces particular skepticism from experts in nuclear physics and planetary science. Dr. Sarah Dodson-Robinson of the University of Delaware has calculated that the energy output required to explain 3I Atlas's luminosity would require nuclear materials in quantities that seem implausible for a natural object. However, she also notes that certain rare radioactive isotopes could, in principle, provide sufficient energy if concentrated through unusual geological processes. While such processes remain poorly understood, they're not impossible within the framework of known physics. The question isn't whether natural processes could create such an object, Dodson-Robinson explains, but whether they're likely enough to account for what we're observing. The probabilities are low, certainly, but they're not zero. Critics of the alien hypothesis also point to the absence of certain signatures that might be expected from artificial objects. 3I Atlas shows no evidence of structured radio emissions, no obvious signs of manufactured surfaces or geometric shapes, and no indications of the kinds of materials that typically characterize human-made spacecraft. If this were a probe from an advanced civilization, argues Dr. Paul Chodas of NASA's Jet Propulsion Laboratory, we might expect to see some evidence of deliberate design, regular shapes, specific materials, perhaps even attempts at communication. Instead, we see an object that, while unusual, behaves in ways that could be explained by natural processes we don't fully understand yet. The debate over 3I Atlas reflects broader philosophical differences about how science should approach anomalous data. Conservative scientists argue for exhausting natural explanations before considering more exotic possibilities, while others contend that artificial explanations should be considered alongside natural ones when the data supports multiple interpretations. Jewett acknowledges the importance of this debate while maintaining his skeptical stance. Science advances by considering all possibilities, but it also advances by maintaining rigorous standards of evidence. The burden of proof for artificial origin is necessarily high because the implications are so profound. As observations of 3I Atlas continue and new data becomes available, the natural explanation camp remains confident that conventional physics will ultimately account for all the object's unusual characteristics. They view the current mystery not as evidence of alien technology, but as an opportunity to expand our understanding of the natural processes that shape objects in the cosmos. The universe is far stranger and more diverse than we often give it credit for, Jewett concludes. We don't need to invoke alien civilizations to explain objects that push the boundaries of our current understanding. We just need to be patient and keep looking until nature reveals its secrets. To understand the true significance of 3I Atlas, we must step back and consider just how rare interstellar visitors actually are, and what their existence tells us about the structure and contents of our galaxy. Before 2017, no confirmed interstellar object had ever been detected passing through our solar system. This absence wasn't necessarily evidence that such objects didn't exist, but rather reflected the limitations of our detection capabilities and the vast scales involved in interstellar space. Dr. Robert Warwick, the astronomer who first spotted Oumuamua using the Pan-STARRS telescope in Hawaii, describes the challenge of detecting interstellar visitors. These objects are incredibly faint, moving very fast, and visible for only brief periods. Finding one is like spotting a single firefly crossing a stadium from several miles away, while you're not even sure which direction to look. The mathematics of interstellar object detection reveal just how extraordinary these discoveries are. Our solar system occupies a tiny fraction of the space between stars, with a gravitational cross-section that represents less than 1 part in a trillion of the local galactic neighborhood. For an object to pass close enough to Earth to be detectable requires an extraordinary alignment of trajectory and timing. Current estimates suggest that at any given time, there might be thousands of interstellar objects passing through our solar system, but most are either too small, too dark, or moving along trajectories that keep them far from our detection networks. The few we've discovered likely represent the tip of an enormous iceberg of cosmic debris traveling between the stars. This rarity makes the unusual characteristics of 3I Atlas even more significant. If interstellar objects were common and we had observed hundreds or thousands of them, finding one with anomalous properties wouldn't be particularly surprising. But when we've only confirmed 3 such objects in human history, having one display characteristics that don't match known natural processes becomes profoundly intriguing. Dr. Amaya Morrow-Martin of the Space Telescope Science Institute has spent years modeling the population dynamics of interstellar objects. Her calculations suggest that the discovery rate we're currently experiencing, roughly 1 confirmed interstellar visitor every few years, is consistent with theoretical predictions about the number of objects ejected from other star systems over the history of the galaxy. Every planetary system probably goes through chaotic periods during its formation, Mauro Martin explains. Gravitational interactions between forming planets can fling countless objects into interstellar space. Multiply this process by the hundreds of billions of star systems in our galaxy, and you get a substantial population of nomadic objects wandering between the stars. But here's where 3I Atlas becomes particularly puzzling. If its self-illumination truly represents some form of internal energy source, it would flip the probability calculations upside down. Natural objects, comets composed of ice and rock, become detectable primarily when solar radiation causes them to outgas and brighten as they approach the sun. This creates a strong selection bias in our observations. We're much more likely to detect objects that follow predictable brightening patterns based on solar heating. An object with its own internal light source would be detectable at much greater distances and wouldn't rely on solar proximity to become visible. This means that self-illuminated objects should be overrepresented in our detection statistics compared to ordinary comets. The implications are startling. If 3I Atlas represents a class of self-illuminated interstellar objects, and if we've detected one in just a few years of serious searching, it suggests that such objects might be far more common than ordinary interstellar comets. This abundance would be difficult to explain through natural processes alone. Dr. Gregory Laughlin of Yale University has developed models exploring this self-illumination paradox. His calculations suggest that if even a small fraction of interstellar objects possess internal energy sources, they should dominate our detection statistics. It's a bit like searching for cars at night, Laughlin explains. If most cars relied on reflected streetlight to be visible, you'd see very few of them. But if some cars had their own headlights, those would be the ones you'd notice first and most often. The fact that we've potentially found a self-illuminated object so quickly suggests there might be many more out there. This abundance problem points towards several possible explanations, each with profound implications for our understanding of the galaxy. The first possibility is that we're witnessing the effects of exotic but natural physics. Perhaps certain types of interstellar objects commonly acquire radioactive materials during their journeys between stars, either through collision with cosmic ray particles or through exposure to the remnants of ancient supernovae. Over millions of years, even small amounts of radioactive decay could provide sufficient energy for detectable illumination. Recent research into the interstellar medium, the sparse gas and dust that fills the space between stars, has revealed it to be far more complex and dynamic than previously thought. Shock waves from stellar explosions, magnetic field interactions, and the debris from colliding neutron stars all contribute to a cosmic environment that might naturally enrich interstellar objects with unusual materials. Dr. Susanna Ductua of the Space Telescope Science Institute has been studying how cosmic ray bombardment affects small objects during interstellar travel. Her preliminary findings suggest that certain compositions could indeed lead to long-term energy storage and gradual release, exactly the kind of process that might explain self-illumination. Think of it like a cosmic battery, Ductua explains. Millions of years of exposure to high-energy particles could alter the internal structure of an interstellar object in ways that allow it to store and slowly release energy. We're just beginning to understand these processes. The second possibility is that we're seeing evidence of artificial objects, not necessarily alien spacecraft, but perhaps the technological debris left behind by other civilizations. Every spacefaring civilization probably loses equipment, launches failed missions, and eventually leaves behind artifacts that continue to drift through space long after their creators are gone. If intelligent life is relatively common in the galaxy, the accumulated technological debris from millions of civilizations over billions of years could create a substantial population of artificial objects in interstellar space. Most would be dark and undetectable, but some might retain power sources or structural materials that would make them stand out against the background of natural objects. This galactic junkyard hypothesis doesn't require that 3I Atlas be an active probe deliberately sent to study us. It could simply be a piece of ancient technology, perhaps the remnant of a failed interstellar mission launched by a civilization that existed millions of years ago. The third possibility is the most profound, that 3I Atlas represents evidence of ongoing galactic-scale activity by advanced civilizations. If sufficiently advanced societies routinely launch exploration probes, scientific instruments, or even automated colonization systems, our galaxy might be crisscrossed by a network of artificial objects carrying out missions we can barely imagine. This idea connects to the concept of self-replicating probes, first proposed by mathematician John von Neumann in the 1940s. Such probes could theoretically explore and colonize an entire galaxy within a few million years, an eye blink in cosmic terms. If any civilization had ever developed this technology, the galaxy should be filled with their descendants. The absence of obvious signs of such widespread colonization has long puzzled scientists and philosophers. Known as the Fermi paradox, this puzzle asks why, if the galaxy should be teeming with advanced civilizations, we see no clear evidence of their presence. 3I Atlas might represent a partial answer to this paradox. Perhaps advanced civilizations are present, but they operate on scales and timescales that make them difficult for younger civilizations to recognize. Their probes might be designed to observe rather than interfere, to study developing worlds without disrupting natural evolution. Dr. Jason Wright of Penn State University, who studies the potential signatures of advanced civilizations, sees 3I Atlas as a possible example of what he calls technosignatures, evidence of technology that can be detected through astronomical observations. We've spent decades looking for radio signals or other obvious signs of alien technology, Wright explains, but perhaps we should also be looking for objects in our own solar system that don't behave according to natural laws. 3I Atlas might be showing us a completely different way to search for evidence of other civilizations. The timing of these discoveries may not be coincidental. Our detection capabilities have reached a threshold where we can finally spot and analyze interstellar visitors, while our theoretical understanding has advanced enough to recognize when objects don't fit standard models. We may be entering an era where the galaxy's hidden population of artificial objects finally becomes visible to us. Whatever 3I Atlas ultimately proves to be, its discovery has already transformed our perspective on interstellar space. No longer can we think of the region between stars as empty and inactive. Instead, we must consider the possibility that interstellar space teems with objects, some natural, some perhaps artificial, carrying information about the history and current state of our galaxy. The bigger picture emerging from 3I Atlas is that our galaxy is far more dynamic and possibly more populated than we ever imagined. Whether through exotic natural processes or the activities of other civilizations, the cosmos appears to be alive with phenomena that we're only now beginning to detect and understand. As our detection capabilities continue to improve and more interstellar visitors are discovered, we may find that 3I Atlas was just the first clear glimpse into a universe far stranger and more active than we ever dared to hope. When we talk about the universe, about the deep sky, about the countless stars that hang above us, there is always a danger of abstraction. Numbers become so large they slip through our minds. Distances grow so vast they cannot be pictured. And yet, every so often, something happens that collapses that unimaginable distance into something real, something close, something that brushes against our own solar system as though to remind us that we are not isolated after all. 3I Atlas is one of those somethings. Think about this for a moment. For billions of years, fragments have been drifting between the stars, pieces of alien worlds, icy leftovers of alien planets, the wreckage of collisions we will never witness. Most pass silently through the void, unobserved, unseen, never crossing paths with another system. But sometimes, through coincidence or fate or simple orbital mechanics, one of these drifters wanders close to us. It enters our skies, faint at first, then brighter, until the astronomers catch it, measure it, name it. And suddenly, an idea that had always been theoretical, matter from another star, is no longer theory. It is here. It is real. 3I Atlas is not the first. Oumuamua was the first to jolt us awake in 2017. A strangely shaped object tumbling through space, accelerating in a way no one could quite explain. Then came 2I Borisov, more familiar, looking like a comet, venting gas and dust as it sped along. Now Atlas joins them, a third traveler, and with it comes a new chance to learn, to probe, to wonder. And unlike the first two, this one gives us more time. Time to prepare, time to aim, time to imagine. In October, it will pass near Mars. This is not a Hollywood close shave, no fiery streak across Martian skies, but close enough that we might, for the first time, see such a traveler from two planets at once. Earth will be watching, of course, its great telescopes in Hawaii, in Chile, on mountaintops across the world, their domes turning to follow this faint point of light. But Mars has eyes too, orbiters circling the planet, some designed to photograph landscapes in extraordinary detail, some meant to study thin atmospheres or surface minerals. If just one of them pivots outward, if the timing aligns, we may catch a glimpse of Atlas from Mars' perspective. And with Earth and Mars both observing, we get something precious. Parallax. The same effect that lets your two eyes judge depth, spread across millions of kilometers. With parallax comes precision. The path of Atlas can be measured more exactly, its velocity nailed down, its spin uncovered. And in that spin, in that motion, lies hidden information. If Atlas vents jets of gas like a comet, if sunlight nudges it more than gravity predicts, these measurements could reveal it. On the other hand, if it drifts in eerie silence, showing no outgassing, no acceleration, then questions deepen. Is it truly inert, or is something else at work? Then comes December, the big moment. Earth itself will experience its closest pass. Atlas will not endanger us. It will not crash through our skies, but it will come close enough that every telescope worth its mirrors will track it, close enough that space observatories, Hubble, Webb, may catch more than just a streak. And for the first time in human history, we may capture images not of a comet from our own system, but of a solid object from another star, resolved enough to hint at texture, shape, perhaps even surface. Pause for a second and imagine what that means. Imagine the first photograph. Maybe it shows a dark, lumpy shard, cratered and jagged like an asteroid. Or maybe it looks smoother, icy, faintly gleaming as sunlight reflects off strange frozen compounds. Or this is the possibility that haunts astronomers. Maybe it does not look like any rock we know. Maybe it looks geometric. Maybe it reflects light in suspiciously clean ways. Maybe, for the first time, we see something we cannot dismiss as natural. The stakes of those images are enormous. Astronomers know what they're after. They want composition. By splitting the light into spectra, they can read the fingerprints of its chemistry. They want rotation because how fast and how steadily it spins can reveal internal structure. They want trajectory to backtrack its origin, to say, this came from that star system, this was ejected from that disk of planets. If they are lucky, They will even find traces of elements we don't often see. Exotic ices from frigid worlds orbiting dim red suns, or complex organics baked into its crust by radiation. Each of these pieces builds a picture. Each turns Atlas from an anonymous traveler into a messenger, carrying news from places we can't yet reach. But once the data is in hand, once we have measured and cataloged, the human mind cannot help but ask bigger questions. What does Atlas mean for us? What is it telling us, not just about itself, but about the galaxy and our place within it? If Atlas is natural, and I'd say it likely is, then it is still profound. It confirms that solar systems are not closed boxes. They are open, messy, violent. Planets form, collide, scatter. Comets are thrown into exile. Stars swap debris across gulfs of space. Our own system has probably ejected countless objects in its long history, each now drifting through interstellar night, waiting to pass near some other unsuspecting civilization. Atlas, in that sense, is karma returned. It is someone else's debris, their version of a comet, now paying us a visit. That thought alone reshapes our sense of scale. We are not isolated. We are part of a galactic ecosystem of wandering matter. And each piece carries information. Like a bottled message washing onto a beach, it tells us something about where it came from. If Atlas is water-rich, then water is common. If it is carbon-heavy, then organics abound. If it carries exotic ices, then its parent star system formed worlds stranger than ours. Every discovery nudges the probability of life. If the galaxy produces water-rich comets by the trillion, then life is more likely everywhere. If not, if Atlas is barren and dry, then perhaps we are rarer than we thought. But then there is the other possibility, the one that lingers in every conversation about interstellar visitors. What if Atlas is not natural? What if it is artificial? Consider that for a moment. If telescopes detect smooth metallic surfaces, repeating geometry, or unexplained emissions, it would be undeniable. Not an asteroid, not a comet, not a rock, but a machine, probe, a relic, proof, absolute proof that intelligence arose elsewhere. That someone else, somewhere else, once looked at their night sky and wondered. That someone else built. That someone else reached out. That possibility electrifies and terrifies. If Atlas is artificial, who sent it? Was it launched yesterday or 1,000,000 years ago? Is it active or dead? Was it meant for us, or are we incidental, just another system it happened to drift past? And more haunting, what happened to its makers? Do they still exist? Do they still watch? Or are they gone, leaving only this silent relic to testify? And that loops us back to one of the great riddles of science, the Fermi paradox. Where is everyone? If life is common, why don't we see civilizations everywhere? Why aren't the skies full of signals, probes, evidence? Maybe life is rare. Maybe we are early. Or maybe most civilizations hit a wall, the great filter, some barrier that few pass. Maybe they destroy themselves in fire. Maybe they collapse under resource strain. Maybe the galaxy itself is hostile to survival at scale. Atlas, natural or artificial, intersects with this paradox. If it is natural, it tells us planets scatter matter easily. Life's building blocks may be common. That would make the silence more troubling. If life should be everywhere, then why aren't we seeing it? But if Atlas is artificial, then the silence has a different weight. It means someone did pass the filter. Someone did reach the stars. But they are not talking, either by choice or by extinction or by rules we do not understand. This is not just about them. It is about us. If civilizations can send probes across light years, will we? Will we endure long enough to scatter our own emissaries into the void? Or will we, too, be silenced before we can? Atlas becomes a mirror, forcing us to ask not just what it is, but what we are and what we might become. And here is the most exciting part. Atlas is not unique. It is only the third we have found, but it will not be the last. In the very near future, the Vera Rubin Observatory will begin scanning the skies. Its vast mirror and wide-field camera will map the heavens over and over, night after night, catching faint moving dots with incredible sensitivity. Astronomers expect it will find dozens of interstellar visitors every year. Dozens. Not one per decade. Dozens. Imagine that flood of data, that flood of possibilities. Each new object will be a chance. Some icy, some rocky, some large, some small. Each a messenger from another star. And with them will come opportunities. We will not only watch them from afar. We may chase them. Imagine spacecraft built not to orbit planets, but to intercept these travelers, to fly alongside them, to take images, measurements, samples. Imagine bringing back to Earth a fragment of an alien star system, dust that formed around another sun billions of years ago. That is no longer fantasy. It is possible within this century. And as these visitors multiply, so too will the unsettling thought. What if one is not natural? What if some are probes quietly slipping through systems, watching, measuring? What if the galaxy is already seeded with such machines, unnoticed until one brushes close? This is the zoo hypothesis, that advanced civilizations watch younger ones quietly, waiting. Maybe Atlas is not for us at all. Maybe it is just passing by. Or maybe it is the test. Will we notice? Will we look closely enough? Will we ask the right questions? Think about how that would reframe everything. Suddenly, every comet, every asteroid, every drifting body could carry secrets. Every visitor would be not just a curiosity, but a potential revelation. We would live in a galaxy alive with watchers, a galaxy where silence is not absence but observation. Whether Atlas is natural or artificial, whether it teaches us about ice chemistry or about alien intention, the fact of it is already profound. It shows us that the cosmos is not static. It is dynamic, alive with motion, filled with travelers. It reminds us that our solar system is not a sealed room, but a crossroads, and it forces us to confront our own future. As Atlas passes Mars, as it passes Earth, as our telescopes strain, as data streams in, we will experience a mixture of wonder and humility. Wonder at what we are seeing, humility at how little we still know. We are a young species, only just stepping into space, watching ancient fragments drift by like messages in bottles. We do not yet know if the bottles contain poetry or code, randomness or intention, but we know they matter. Atlas will not wait for us. It will speed on into the dark, back into the same void from which it came. But the questions it leaves behind will remain, haunting and inspiring. What else is out there? Who else is out there? What will we become? And perhaps most of all, when the next traveler comes, and it will we be ready? Because this is only the beginning. In the decades to come, as the Rubin Observatory and others flood us with new discoveries, we may look back on Atlas as the moment when the story began to shift. When humanity stopped seeing itself as alone, and started to understand that the galaxy is full of whispers, drifting through the dark, waiting for us to listen.